Welcome to the second day of the RNA-seq section of the workshop. Today we'll be talking about differential expression analysis, and this first video will be giving a brief introduction to differential expression. The goals of this video are to present a brief overview of the different approaches to differential expression analysis, as well as think about some considerations for choosing a program or programs. Differential expression requires us to compare data sets. So in the simplest case, our goal would be to test expression levels for different genes under two different conditions and determine if those genes are expressed differently according to some statistical test. When looking at RNA-seq data sets, we first have to decide how to determine expression levels. Most programs use counts over a specific feature as a proxy for expression. But one issue with using counts is how do we normalize for differences between the different data sets? And that leads into second question is how do we determine if they are different? And this gets even more complicated than just having to normalize for some biases such as different number of total reads, but also how to account for biological variability. So this brings us to the steps for differential expression analysis. You first have to start with read mapping, and this was covered yesterday when we went through the top hat aligner. The second step would be to, again, get your estimates for gene expression. And as I said, many of the programs use counts. So however many reads mapped to each gene or each exon would be the number of counts for that gene. There are differences in how counts can be computed depending on what kind of boundaries you want to set. Some programs will be more conservative than others, and this may affect your downstream analysis. The next step would be to perform some sort of account normalization, and again, as I said, there's many different biases in data sets, one of them being how much total sequencing you have for each data set. But you also have biases within the gene length, mapping biases, and other sorts of biases. Some programs do better jobs normalizing across many of these, whereas others stay fairly simple and just do some normalization across the total number of reads. And lastly, you have to perform your differential expression analysis. And this would be, again, where you're setting some test statistic and determining whether your expression levels are statistically different between those two conditions. We've mentioned several times that replicates are very important when performing RNA-seq, especially for differential expression. And this is because we have to get a measure of the variation in the data. We can only do this with replicates. It turns out technical replicates have quite a low variability. It can actually be modeled with a Poisson distribution, where the mean is equal to the variance. But when we look at biological variation, what we actually see is there's a higher variability. What you see in the figure on the right is the straight line, red line, is actually the Poisson distribution, where the mean equals the variance. And this is it would be a measure of the technical variation. The biological variation is shown with the points, and as you see, the variance is larger than the mean. This is something that is called overdispersion. Many of the current programs actually use the negative binomial distribution to account for overdispersion in RNA-seq data. And they use this distribution to get an estimate for the variance between biological replicates. When we look at differential expression analysis programs, it turns out we have a lot of choices. There are actually more differential expression programs than there are mapping programs, and they vary in many different ways, starting with input data. Many of the programs take read counts as their input, but there are some programs that take FPKM as a measure for expression, and some programs take even other data. All programs have slightly different methods for normalization. Some work better for highly expressed genes, others work better for lowly expressed genes. Additionally, while many use the same basic statistical model for count distribution, how they actually estimate the parameters to go into this model can vary quite significantly. Additionally, the statistical test for calling differential expression can vary between programs, and some programs are actually able to look at different isoforms in differential splicing. Because of all of these differences and differences in RNA-seq data sets, some programs work better for some data sets, whereas others will work better for other data sets. And really the only way to get a true handle on this is to use several different programs for your data, have a good idea of the literature, and read some of the benchmarking papers. I'll be putting several benchmarking papers on the website for you to take a closer look. So we'll be looking at 2 programs in the rest of this workshop. The first program we'll be looking at is DESeq. This is a very popular program for basic differential expression analysis. It's been found to perform fairly well across many different types of sample sets. It uses counts for gene expression, and it calculates a size factor that it uses to normalize for the differences in sequencing depth. It also uses the negative binomial distribution to estimate biological variance, but it can only look at annotated features. And this package uses the popular R programming language that's very good for statistical analysis. The second program we're going to be using is Cufflinks. Cufflinks is actually quite different from DESeq. It actually looks at differential splicing, and it was the first widely used program that was able to look at differential splicing. There are other programs that have been coming out that are able to do this, but Cufflinks remains one of the easiest to use. It performs assembly and computes expression measurements of assembled transcripts, and it uses FPKM as a measure for the expression of those transcripts. But it is a fairly complicated pipeline. It actually involves 3 different programs: Cufflinks, which does the assembly and expression measurements; CuffMerge, which is used to merge different assemblies together; and CuffDiff2, that is used for differential expression. CuffDiff2 can be used on its own. It uses a beta and negative binomial distribution, and it does this to account for variability across both genes as well as transcripts.